Hiya and welcome to day 19 of the 24-day physics extravaganza of questions. Okay, so what we've got here is a magnetic fields question, and it's quite a wordy one at the start. So figure 1 shows the arrangement for an investigating of the electromagnetic induction. When the switch is closed, there is current in the coil in circuit X. The current is clockwise in direction and viewed from position P. Circuit Y is viewed from position P. Explain how Lenz's law, so it's explained, so you need to be saying because. So explain how Lenz's law predicts the direction of the induced current when the switch is opened and when the switch is closed. And it's a 4-mark question. So there's clearly 2 things they want you to talk about. Firstly, when the switch is open, and secondly, when the switch is closed. So you're going to dedicate 2 bullet points to each one, okay? So first of all, it says explain how Lenz's law predicts. So the first thing I'm doing is I'm going to state Lenz's law. So Lenz's law is when the current induced opposes the change that caused it. Okay. So the first thing is we want to talk when the current is, the switch is closed. So when the switch is closed, so this is the closed switch. Ooh, can't spell today. Sorry, difficulty earlier as well. Closed switch. So here, the coil becomes a current carrying wire and generates a magnetic field. This change in flux induces an EMF and therefore a current in, what's it called, circuit Y. But the flow is opposite to the flow in X. When you open the switch here, the change in flux, instead of increasing, is decreasing, okay, is in the opposite direction. Therefore, the current induced will be the other way to before to comply with Lenz's law. So it's asking you here, explain how Lenz's law predicts. So what I'm saying here is that the coil becomes a current. I'm stating what Lenz's law is. So the coil becomes a current carrying wire, generates a magnetic field. This change in flux induces an EMF and therefore a current there, but the flow is opposite to the flow in X. So the flow is opposite to the flow in X to obey Lenz's law. Okay. When you open the switch, the change in flux is in the opposite direction. Therefore, the current induced will be in the other way to before to comply with Lenz's law. So if we actually look at the mark scheme for this here, wrong question. So the mark scheme here, they want you to mention Lenz's law. So normally when they go, why would Lenz's law? State Lenz's law. Okay, so when the switch is on, the current increases the flux through Y, which causes the current in the opposite direction of the flux here. When the switch off, the current through Y, X decreases, so the current travels in X to create flux to oppose the decrease. Okay, so what I'm doing there is I've explained Fleming's Lenz's law. Wrong pen. I have explained Fleming's law. I talked about the fact that a current carrying wire generates a magnetic field, and this change in flux induces an EMF, and therefore the current in Y is opposite to the flow in X. Okay. Which, if you go back to the mark scheme here, goes to switch on, the current increases the flux through Y, the change in the opposite direction anticode that flows in the flux. So yeah, I've got one mention of gradual field, there's a change in flux. Okay, when you opposite change it's in the opposite direction, therefore the current induced will be in the other way to comply with Lenz's law. Okay, to oppose that change. Bit of a wordy question. But it's one of those things. If you mention that if something's talking about why is something induced a current, if you actually mention that something's experiencing a change in something, normally a current carrying wire is generating a magnetic field. Therefore, if something experiences a change in flux, it will induce an EMF, it will induce a current. If you can say those kind of things, even if you don't know what you're talking about, you can pick up a few marks there. Okay, so an earth inductor consists of 500 turn coil in figure 2 and 3, and is set to measure the horizontal component of the Earth's magnetic field. When the coil is rotated, now this is important, the word rotated, an EMF is induced. The mean diameter is 35 centimeters. The figure 3 shows the output here. It's asking here, determine the flux density of here. So when you're dealing with the word rotating, and when I say rotating, I mean it's spinning around and around and around, not just going from this position to this position. It is spinning round and round and round, and you can tell that here, okay? Use the formula EMF equals B-A-N omega sine omega t. And really importantly, we know that the maximum EMF, okay, is where this equals 1. So you've got B-A-N omega. Okay, so I'm trying to find B. From this graph, I can find the maximum flux, the maximum EMF that I generate. And that's going to be about 5.6 microvolts. So Emax is 5.6 microvolts. So 10 to the minus 6. Okay, my area, so it's a circle with a diameter of 35 centimeters. So its radius, 0.35 divided by 2 is 17.5. So that's going to be pi times by 0.175 squared. And that's going to be 0.096. N is 500. And omega is going to be 2 pi, okay, over t. So I need to find the time period of one oscillation. I can't do that. It's a bit awkward in this one. But I do know I get 1.5 waves in 1 second, okay? So I get 1 lambda in 203, so 0.67 seconds. Okay, so I've got my time period. So my omega here is going to be 2 pi over 0.67. So 2 divided by that times by pi. Oops. And I'm going to get 3 pi. Okay, so that is 9.42. So here, I know if I just zoom down a little bit, I've got B is going to be equal Emax divided by A-N omega. So it's going to be 5.6 times 10 to the minus 6 all over 500 times by 0.096 times by 9.42. Okay, so 5.6 times 10 to the minus 6 divided by the answer divided by 500 divided by 0.096, and I get an answer of 1.24 times 10 to the minus 7 Tesla. Okay, just grabbing the mark scheme for this one here. So they've got 12.4 nanotesla. Yep, that's right. I've got 1.24 times 10 to the minus 8 there. Okay, so again, you get 3 marks. One, if they can actually see you work out either both the omega and the peak V from here using the formula I said here and then getting the answer there. Okay, so remember, if you got a line, you should put it on here. So I've got 1.24 times 10, minus 7, minus 8. I can't do it. It's minus 8 on my calculator. I'm just going a bit bananas. 1.24 times 10 to the minus 8 Tesla there. Get 1 mark for finding this and this, 1 mark for the maths, and 1 mark for the answer. So there we have it, a very simple but a bit wordy question on magnetic fields.